Okay, today we are going to do a simple example of a cantilever beam using Patran to generate the model as well as to do the finite element analysis. Of course, there is the first thing we should do is to examine. This is the screen as you open the Patran program. It has several tabs, and here you say home, it has geometry, properties, loads and boundary conditions, meshing, analysis, and results. We're going to use all these tabs and all these steps to be able to produce this model. The very first thing we got to do is we got to create the geometry of the model. In this case, we're going to create a simple cantilever beam. So what we're going to do is we go here to create. We're going to choose to create an area, a simple cantilever beam with plate elements, whether they are triangle elements or quad elements. So plate element with thickness. So the first thing we're going to do is let's create a couple of lines. And to do that, I put here in curve, and then I am going to click in here, which is the screen position. And then I click in one screen position, and then on another screen position, creates a line. Then I click in one screen position, and another screen position creates another line. So now that we have this line, we can create a surface. Surfaces could be created in many ways. As you can see in here, you created the curve, so I'm going to create the surface. There is a method curves. There is edges, extract. There is a bunch X, Y, Z. You could specify the coordinates. Many ways you can do it. So in this case, we're going to do using these two lines. So I click on the first line, click on the second line, and I got my surface. I'm going to move this a little bit so that you realize we're working in 3D. So you can see the axis down here. And so once we have this surface, we are basically done with our geometry. I think we need to break this geometry into finite elements. So we're going to go to where it says meshing. Okay. Right now in general, this could be, this is a 2D model, but you have a complex system, and after you created the geometry, you need to go to this section where it says meshing. So we are going to create the divide this region into finite elements, and the way we're going to do it is, seeing here it says by default it says mesh seed. This mesh seed, it indicates to us which way, on which side, we can specify how many elements we want, how many nodes we want on the end. Based on the edges that we specify, then the number of finite elements would be determined to the whole region. So by default it starts at 2. Maybe we'll do it here. We'll say, oh yeah, this is good. See, 2 elements, it's got 3 nodes. Let's put this to the other end as well. And then maybe on this one, I'm just going to go and do more elements because the side is longer. I'm going to go to 8. 8, yeah. So with 8, I click over here and watch what happens. See? Goes 1, 2, 3, 4, 5, 6, 7, 8 elements, and of course 9 nodes. Same thing here. So at this point we have seeded, you may say, our region so that we can create a mesh and divide the region into finite elements. So that's what we want. We would like to break it down. So now, after we have done this, we are going to go to where it says mesh. So we did the seeding, you may say, or what we want. But now we are going to create the elements themselves. So you see, by default, they are, when you say surface, the computer gives you two-dimensional elements. If I had a solid in here, see, it gives me other choices of elements, wedges, hex elements, things like that. But let's keep in mind, I don't want to confuse things. This is a surface, 2D, either quad elements or triangular elements. So we're going to go with triangular elements. And at this point, we need to pick the surface. We select the surface, and then we need to say apply. And lo and behold, the computer, based on the seeding we did, creates this set of finite elements. Now, we have several other steps to follow. We need to create the loads and boundary conditions. So we would like to fix this in and put some loads over here. So what we're going to do is we go to where it says loads and boundary conditions, and then here we create the constraints. You know, the boundary conditions are basically constraints. So the displacement first. So I am going to give a name to the displacement set. Let's call it displacements. And that's the name of the set because this is, you could create several conditions. You know, could be simple supported, could be support fixed on one end, and which what we're going to do. And using the same geometry, you could potentially create several models. That's why we need to give names. And then later on, we build a case that has all those names. So the input data is what we need now to create that set that says displacement. So I am going to say, we click on the input data button, and then I am going to do, okay, zero displacements in here. And then, no, that's the translations. And I'm going to say 0 rotations. Okay, so 0 rotations. Let's click OK. And now, input, select the application region. This is a crucial step. And I am not sure if last time we might have overlooked this, and I wanted to emphasize it now. Do you see that button on the right hand side, what it says? It says geometry, right? But think about what will happen if the loads and boundary conditions are on the geometry. How do we have control on which nodes we want the loads? So it doesn't make sense to keep it on the geometry, but rather see where it says Finite Element Model, do that. And then in here it says selected nodes, because if we kept it on geometry, it says selected geometry entity. What we want is the Finite Element Model, because we want to fix this node. See right there? Okay, I selected that node, and you say OK. And now we say apply. And it says the click, yes. So I select, that's how I selected, that's how I fixed this in. And now we are going to put the couple of loads over here, and I am going to go and do in the same loads and boundary conditions, we are in creating force. When we do this, the computer wants to know a set name for the force, so I'm just gonna call it forces. Yeah. Then same procedure, it needs the input data. If we want to put the loads over here, then it makes sense to specify that the loads are going to be in the minus z direction, in the minus y direction, right? I'm just making that a little bit so that you'll see it well. So this would be a 0. Then we have a minus, let's do 1000, and then 0 again. That means we are specifying loads of 1000 units, and then in the minus y direction, but nothing in the x and z. And also we are not specifying rotations in there, so this is going to be 0, 0, 0 in here. And so we say, okay, and then it's going to say select the application region. So we select the application region, and we're just going to put them on this side over here. See those guys? See, selected those nodes. Click OK. And now we're ready to say apply. And it will actually do it. Okay. So I believe this is, we are ready to proceed further, but want to make sure that everybody is on the same. Okay, so now we have this cantilever beam. It's fixed at this end, and it has the loads over here. Now we need to use the other tab where it says properties, because we need to specify the materials and the properties for each one of these. So we says create. We need to do the property name. I'm just gonna call it, why don't we call it property? Okay, so that's my set of properties. I'm gonna follow the same logic here. Input properties. So we need to have the material name. Give the material name. I'm gonna give it a steel as the material name, and I'm just not gonna put anything about orientation because I want to be isotopic material. Thickness 1. How is that? So we have this, and with this specify the element not selected. Okay, so okay. We need to also specify the, okay, so there's the element properties. You see what it says isotopic here? Here's where we need to call it material. Let's call it material here. Material name is steel. And then input properties. You see, now we gotta tell it what material has this. Modulus of elasticity. We have to define the modulus of elasticity for this. These are the properties that we need for the material. So we're going to put 30 times 10 to the 6th. And then we need to do the Poisson ratio as well. In this case, we're going to put it 0.25. Then we click OK. And then, of course, we need to finish putting the material properties and data. Let's just go to the next button. We test that. We don't need to change it, so we click on apply, and then we need to go and do the finish up the properties here. So we are on properties, and then we need to, I think we click on apply. Let's see what else we're going to do. I think we have finished the material properties, so that's the tab that we go to, and what we need to do is to establish what the entire region that applies to this. So let me make sure that we have a material name that we called it still. We're gonna go and now with this select the whole application region, so that's the next thing we're gonna do. We have to select the application region, we select the whole thing with clicking the mouse on one point and then dragging it over, and therefore now we are ready to click OK in there, click on apply to make sure that this is the newest part of the database of our model. So one of the things that you can see in here is that all the elements are triangular here. We're going to go to the analysis part now. So this is where we're going to generate the matrices for the solution of the nodal values. So we need to go over here and click on the analysis in the entire model. We keep that and then full run. So we gotta check all the little things here. Say job name is example in there, and then I don't think we need to do anything with the translate the parameters, but just so we can see it, these are the parameters that the precision parameters that may have might be specified. In this case we are not going to change anything really, so we need to just verify that in other words, pick up the default values. So click OK, and now we are gonna say, what about the solution? The solution is linear static solution. You could have all those other ones that are listed there, but that's not what we're doing. We're not doing vibrations or transient response or frequency response, things like this. We are doing a linear static solution for a bending of a beam, and therefore we don't need to change anything. So click on OK, and then we are going to look at the other buttons just in case. I don't think we're going to need any of that in there, the second one. Then we're going to go to the subcases button, because we need to establish which case we're going to analyze. So in this case we go on, we really should have the name of this, like a case 1 type of thing. So you see where it says name for the case. We need to do that. Okay. So we are saying that these are the solution that we want, and then we are going to go and say apply, and then it says there is a message here that the subcase title is blank, so we need to fix that right there, the name of the case. So let's put the name in there and then click on apply, and then click on case 1, and we'll have to say okay, apply, and so now it has the name. Click on the yes, and so now we have the verify the case. So case select, I think we've already done that, but just in case I just will stay on 1 just to examine the options here. So case 1, and then at this point we are ready to submit the job to Nastran, and that's exactly what's happening right now on the screen. The matrices have been generated, they're generated and then sent to Nastran for analysis. Now the whole set of linear equations has been resolved by now. In 2D, let me remind you that we're looking for two variables, x and y, because in 2 dimensions we are defining the region in 2D at this point. So now we gotta go and take a look where the results are. So we go to analyze and access results, and now we're gonna have to go and look for the to select the results file. So that's the next thing that we need to look at. That is the select the results file. Do you see that button on the bottom? That's what we're gonna do in just a moment. Hopefully that results file is there. So there we go. Click on select the results file, and now it's going to come on the screen, and sure enough we have an XDB file on the job called example, which tells us that the results were generated by Nastran, and so now we need to read them. We have accessed the results, and then we click on apply, and then now we are going to go see where the bottom at the top is results. Click on results, and when we see those 2 lines on the right, that's a very good sign, because if we click on one, it will give me all the solutions that the computer calculated for this particular example. So there will be displacements, rotations, stress analysis, a bunch of results, and there it is. We pick the displacement, vertical translational displacement, and that makes sense. The displacement is the highest on the red region, and it goes all the way to being 0 at the left. So you can see there I'm going through the model and displaying the different finite elements. What I want to emphasize in here is you see how the red fringe and the orange fringe are generated. They are generated by 2 points that cross the sides of the triangular finite element. And so if you do the same thing to the neighbor, then pretty soon you can define the region. The region that has the level of deformation or level of stress by coloring it. So that's how those fringes are generated. So you see how the finite elements are. Every boundary of the color crosses 2 points on the triangular element. And those 2 points would allow the computer to calculate which way it should color the picture, because the color is completely related to the level of the variable, level of the stress, from dark blue to red, whereas the red is the highest level of deformation. So this was successful. We could take a look at other kind of results, and if you click on another one and click on apply, you will see that we have different choices in there, and so you will see in a moment you will display different things. I think this one also has to do with the displacements, but I believe are the rotations of the nodes, because and this was definitely is the translational displacement, meaning the displacement in downwards in this case because of the load. So I'm just playing around with different solutions that the computer offers me in that list. This, for example, would calculate the stress. So you can see the higher stress concentration would be at the top left corner, because that's where it joins with the wall and it has the biggest tension. So the picture makes perfect sense. So we're displaying different ones so you can actually see it. You could also do an animation of this, and you see the little button on the on the left button that says animate. If you click on that button and then you click on apply, this picture and the color changing will become a dynamic changing picture. So we have, now that we have been successful, we can investigate many of the solutions and see which way we like that, whether it makes sense or not. So that this is the point where the design process occurs, because by now you have done your geometry, your finite elements, and you did the loads, and with all that information we were able to generate this finite element model. So that has been the finite element model from beginning to end.